Now we want to find the work done of the two special forces. We would just want to find the work done by the weight and the work done by the resultant force of the spring. And then we're gonna introduce about the potential energy of these two types of the forces. Let's just start from the first one. Okay, the work done by the weight, right? Example. So let's consider that if we have a plane here, okay, so let's say the ground, and then just make this ground to be the reference level, okay, and then initially we have an object is at this position, and overhand just grab the object. So let's say that if the object, right, is at the distance y1 from the reference level, okay, and then sometime later we try to place the object in the upward direction and then go to at this position. So then here it's going to be the new position of the object relative to this reference level, okay. So now we just assume that if we raise the object with the constant velocity, okay, so the object rises up with the constant velocity. In this case, it means that the net force exerting on the object, right, must be equal to 0. So which force do we have here? Okay, so let's say that we have the weight, okay, we have the weight equal to the mg, and then we have the normal rotation force, right, it's be the one that we use that try to lift to push the object in the upward direction. So this force just point to this direction. Okay, so let's say that this is let me just write down as the Fext for the external force, but let me just keep in mind that this is the normal rotation force. Then we just want to find the work done by the weight, okay, we just want to find the work done by the weight. Then by definition, right, the work done by the weight, Wg, okay, is going to be equal to, okay, it's just equal to force and then dot product with the displacement, right, because in this case the force is constant, we can use this equation. So we have the force dot product with the displacement are just equal to the F, and then times the displacement, and then times the cosine theta. The theta is the angle between the force and the displacement. Okay, now force, okay, we talk about the weight mg here, okay, so mg and then times the displacement. In this case the object is displaced from the y1 to the y2, so the displacement is the y2 minus the y1, okay, and then times the cosine theta. So now for this mg, the theta is equal to the 100 and the 80 degree, right? Why? Because you can see that the mg just going down, okay, the mg just going in the downward direction, but then the displacement, right, the displacement just the y2 minus the y1 in the upward direction. So that's why the angle between the mg and y2 minus y1 is 100 and the 80 degree here. And we know that the cosine 180 degree equal to the -1. Then finally we can say that, okay, the work done by the gravity or by the weight, right, it's just equal to minus sign, confirm this one, and then let's just multiply the mg to the y2 and the y1 here. So we have the mg y2 minus mg y1, okay. But now if we just want to consider the work done by the resistance force, right, that we use to lift the object, it means that it's going to be the work done by this one, the external force. So just do the same thing, but now you can see that the direction of the external force, right, just opposite to the mg here. Then we should get the same equation, but the difference between the work done by the external force and the work done by the weight should be the minus sign here, right? Because this minus sign just comes from the opposite direction of the y2 minus y1 and the mg. But now for this case, the external force have the same direction as the y2 minus y1. So we should get the plus sign for this. So we have the work done by the external force equal to mg y2 and then minus the mg y1. Okay, I think it's just good to define the potential energy due to the gravity. Okay, so let me just write down here, define the potential energy due to the gravity. Okay, so let's use a symbol as the U sub G here, the potential energy due to the gravity. What is that? Is this the energy? Okay, it's a type of energy which is stored inside, okay, an object, okay, as raised no wait as displaced, should say displaced from a reference level, okay, to resist the gravity. Okay, so that's called the potential energy due to the gravity. It is the energy stored inside an object as displayed from a different level, okay, to resist the gravity. For example, in this case, okay, if we look at this hand, right, you can see that, okay, let me duplicate it. Oops. Okay. Okay, if we say that if the ground is the reference level, and if we just put the object on the ground, right, so it means that there's no potential energy, because I mean here the object will be stable, right, to stay on the ground. But if we just move the object going up and more, okay, so the more the object go up, then the more the potential energy will be stored. Okay, so that's will be the idea. So we say that, okay, the UG for the potential energy due to the gravity, right, equal to the mg and then times the y. So this y, okay, so where the y is the displacement, the displace of the objects, okay, from the reference level, as I just mentioned before. But one thing that you need to keep in mind is that the reference level shouldn't be it's not necessary to be the ground, okay, it can be somewhere above the ground or it can be somewhere under the ground. Okay, so that's called the reference level. It just depends on the how we can identify it. Okay, so if we look at this equation, right, we say that the work done by the weight equal to minus the mgy2 minus the mgy1. Then we can just find the relationship between the work done by the weight and the change in the potential energy as, okay, the relations between the work done by the weight. Okay, so WG, right, the work done by the weight, and the change in, okay, the change in the potential energy due to the gravity is. So okay, WG equal to, okay, so this one is UG for the second position, this is the UG for the first position, right, for the initial position. So then we have the minus of the UG2 minus the UG1, okay, which is equal to minus of delta UG, right? Actually I should write down here, oops, yep, something like this, and then equal to this one, right, and then equal to minus of the mgy2 minus the mgy1. Okay, so let's look at these examples. Okay, so let's look at this example and see what we can get from this one. Okay, so we have object, so let's say a rock here with the mass equal to the 1 kilogram, right? Initially is on this position, the 5 meter, and then if the rock is raised to the 15 meter here, okay, if the rock is raised to the position of the 15 meter, we just want to find the initial potential energy, the final potential energy, and then the change in the potential energy here, and then we can change the reference level. So let's try maybe 3 reference levels. Okay, so the first of all, let's just make the reference level to be negative 10 meter here. Okay, negative 10. Let me use the blue one. Okay, so now we say that if the reference level is at the negative 10 meter, right? So let's compute for the U1. The U1 is equal to the mg and then times the y, right? So the mass equal to 1 kilogram, and g is in this case, let me just use 10 so we can just calculate it quite easily. Okay, so the g, let's say, equal to 10, and then from the y1, right, the y1 is the displacement from the initial position to the reference level. So in this case, the y1 is equal to what? Is equal to the 15 meter. Okay, it's just equal to the 15 meter here. Then we can get the u1 to be equal to the 150 joules. Okay, actually I have the unit here already, so let me just delete this one. Okay, 150 joules. So now for the u2 at this position, right, we just do the same thing. We have the mg, okay, and then the y. The y is equal to what? Equal to 25, right? Because from the negative 10 to 15, it's just equal to the 25 meter. Then we can get the u2, right, equal to the 250 joules. So now to find the delta U, the change in the potential energy is going to be equal to the final potential energy minus the initial potential energy, right? So we have the 250 minus the 150, which is equal to the 100 joules. Okay, so this can be the change in the potential energy of our rock here. Okay, so now let's try, okay, if the reference level is at the 0 meter. Okay, so let's try at the 0. Now for the mg, right, mgy, so mg and y here, so the y here just equal to the 5 meter, right, because the y is the displacement of the object from the reference level, which is equal to the 5 meter. So we just multiply by 5, and then it's just equal to the 50 joules. So now for the final position, we have the m, g, and then the y. So this will be the y in our case, right, equal to the 15 meter. Okay, equal to 15 meter, and then equal to the 150 joules. Then again, right, we can get delta U to be 150 minus the 50, which is equal to the 100 joules. So you can see that delta U just the same, right, but the U1 or the U2 are differences. Okay, so now let's try this. If we have the reference level to be here, okay, at the 20 meter, so we have the reference level at the 20 meter here. So okay, for these two cases, right, the initial and the final position will be below the reference level. Okay, so let's find the U1. We have the m, g, and then we have the m, g, and then the y, right? In this case, this is the reference level, so the y here must be equal to what? Must be equal to negative, okay, negative 15, right, because from 20 to the 5 it's just equal to the negative 15. Then we have the U1 equal to minus 150 joules. Now for the U2, right, we have the m, g, and then y2. In this case, y2 is just equal to minus 5. Then we have equal to minus the 50. Okay, minus 50. So now we just want to find delta U, right? Delta U here equal to the final value, right? Final potential energy, and then minus the initial potential energy. Then again, just equal to the 100 joules. So then, what can we conclude from these three examples? Okay, what can we conclude from this T example? So we can conclude that let me use the symbol. Okay, we can conclude that the potential, the values, I would say the values, okay, of the potentials energies, right, it just depends on the reference level. Because you can see if we change the position of the reference level, you will get the different potential energy, right? Even though it's just the same object and the same position, you still get the different potential energy. That's be one thing. And then the other thing is that the potential energy can be positive, 0, or negative. Okay, it can be positive, 0, or negative. This one will be different from the kinetic energy, which will have only the positive value, right? Because for the kinetic energy we have mass, which is positive, and the v square, which is positive as well. So the kinetic energy must be always positive. But now for the potential energy, it can be positive, 0, or negative. Okay, then the last one is delta U, right? The change in the potential energy doesn't depends on the reference level. Okay, it doesn't depends on the reference level, so you can see that even though we change the reference level, we still get the delta U, right, to be the 100 joules here. Okay, so it means that delta U doesn't depend on the reference level. Okay, so then in this case, right, you can see that in this case we can see that the work done, okay, the work done by the gravity on the rock, right? So we said this is the rock. Okay, the work done by the gravity on the rock is, okay, then from equation Wg equal to minus delta Ug, right, which is equal to minus the 100 joules. Okay, and that's it. So this will be the answers.